going on into this, scientific journey, we have as next guest Professor Christian Maywald from the Technische Universität Chemnitz. He will talk about motion analysis, modern technologies, assessment tools, pros and cons, postures. So as you see, during the summit today, you have seen some solutions. So now we are, considering all the back effects and all the possible impacts on the human beings and also from a legal perspective, because there are a lot of aspects to be considered. So I hand over to Christian. Christian is another new member of our EAWS Scientific Committee. So I give you a warm welcome, and I hand over to you, please.
Thank you, Gabriele. Can you hear me? Can you see the slides?
Yes.
I believe we can. Yes. Okay, so let me take a little turn into the motion analysis technologies employed in many of the aspects that the previous speakers already touched. So when we talk about motion analysis technologies, the focus is put on technology more often than we might like to. And I will take a turn also in my talk to lead you to some more questions that arise from technologies, not just by different application scenarios, but also from the output they deliver. So when we talk about human motion analysis, this is something probably many people are familiar with. You have seen some sort of instrumented analysis, especially motion capture. This originated in the late 19th century, basically by imaging technology. So advances in photography made this possible, and what it delivers is usually a representation of human movement, and you can measure the aspects of your image and often relate it to a real world scale. And this will be applicable in many scenarios. For instance, it has been driven by medical and especially sport performance issues, but also developed into some very important branch, for instance, in gait analysis and medical rehabilitation. So capturing motion is usually done using a traditional workflow. If you have a look at this picture, there's 4 cameras implemented in this setup, and there's a subject which is instrumented with these tiny little markers you may have seen in other contexts, and these cameras are able to actually track the position of these markers, automatically identify them, record their position, and these positions are then transferred to a so-called digital human model. So this model is as you can see, quite simplistic representation of this real world person, and it's comprised of more or less many rigid bodies. So in this case, for instance, the foot and the hands and the head are represented as a single rigid body, and these are interconnected. And so anything captured through motion capture systems will more or less go through this process of capturing real motion, transferring it to some kind of human model, and then the model will create, or based on that model, an output will be created that looks something like this. Most of the cases, you get an information. In this very simple case, it's an angle of the knee joint over time of a walking person, from foot strike where the knee is slightly bent to the swing phase where the knee is flexed way more to make to clear the surface and to make it possible to have the next stride and the foot in front of the subject. In many cases, there are additional parameters covered, for instance, forces or muscle activity. Pia Maria has covered that a little bit. And there's basically several different concepts of covering these properties. referring to motion capture, this is basically driven by camera technology. If it's as you can see here, it's quite cost intensive, requires lots of space, and usually is also very restricted to certain fields of application. So especially in confined spaces or outdoor environments, these systems often don't perform very well, and you need alternatives to that. Over the recent years, the aforementioned inertial measurement systems have developed and matured. So these sensors are self-contained units. They can track rotational velocity and acceleration, and you will find these sensors attached to the body. So this is an active sensor in comparison to the little markers you saw earlier on the subject in this camera scenario. There are certain advantages and drawbacks with this solution I will cover in the next slide. So I want to point out some other technologies that may be less well known, and they're actually far older than the other two, or at least as old as I think the electromechanical devices like goniometers, which are basically tracking motion through strain gauges and applying these to a two-segment joint model like here with this elbow will enable you to track motion as well with a totally different technological concept compared to the other two approaches. So the problem with these approaches is that inherently they generate different consequences for what you get from these approaches. So the camera-based systems, they are actually tracking your positions, position of the subject or the body over time, and the weakness involved in that is the model output, so the complexity of your model, and the model output will be more or less accurate given the complexity of your model or the in-depth modeling approach you take. So the resolution, the technical accuracy of this system is not the main problem. It's more of the spatial requirements and the applicability in certain situations. So the inertial systems, however, they suffer from an entirely different problem in that their tracking accuracy is kind of compromised by their principle of measurement. So they don't track position in space, they track acceleration and rotation velocity. So in order to calculate and estimate a position in space, you have to employ a set of complex mathematical procedures, which may add up the more distant your sensor is placed from a certain origin of your model, and the more, for instance, the more wildly the movements are being carried out that you want to record. With a third technology, the main problem consists in that the entire device is not capable of detecting motion in itself. So it's just a relative motion or a relative change in angular position. So this might be an approach for really specific and local motion capture tasks, and is certainly not usable for like full body motion capture as you would expect in camera and inertially based measurement systems. So and this goes back to what Gabriele mentioned at the beginning of his introduction. It is probably very important to differentiate between the scenario of application you're aiming at. So motion capture technologies will differ and may differ if you are like in a conceptual phase up front, where you make predictions, where you do simulations of movements of basically workplaces that don't even exist yet, compared to real-world empirical assessments. And this is what we do. I'm with a Department for Human Movement Science, so we rather not simulate movement, we capture real movements and try to evaluate the actual real-world movements that are taken by, for instance, workers, evaluate the risk this contains, and probably detect effects of interventions to deal with this risk situation. So technology-wise, if we want to sum this up as a midway point, the technology itself is diverse, and you will be able to find a technology that will cover the specific field of application you're looking for. They have their drawbacks and benefits. All of them have this, and there's no better or worse system without looking at the set of the scenario you're going to use it in. The problem with digital human models is with all these approaches. So this is kind of a hinge point, the more complex your model can be, the more costly it will get to power the model or to feed enough data to the model to produce a meaningful output. But on the other hand, the output could be way more informative than the one generated by simpler models. And what is rarely pointed out, that all these results you see, is it in maybe from scientific presentations to presentations done in the industry, the result of a motion capture or motion analysis procedure is always a model output and is not the real human movement that actually occurred. This depends, they may be closely related to each other, but it depends on the complexity of the human model that is employed. So this would be a very short talk if I would just only focus on technologies, which I think is not the main problem we're facing today. There's two more problems I want to address, and possible solutions are sometimes easy, sometimes rather complex, and the limitations that may seem very, very prominent, they might be overcome using a slightly different approach to what has been done in the past, especially regarding scientific studies on, for instance, ergonomic interventions in workplace design. So the first of these problems is the variability of human motor control. I will get to that in a minute. And the second problem is, how do we generate evidence for interventions or for any changes we apply to workplace design to demonstrate its feasibility? And Francesco has already pointed out the long-term versus short-term effects, and especially with safety concerns in exoskeletons. So looking at human motor control, you will see that if you ask a person to repeat a motor task, and this may be true for, or is true for, walking as well as lifting, and in this left slide you see repeated trials of a single person walking, and this is the same angle you saw before. It's a knee angle during the walking cycle, and depicted by the icons below. You can easily match the specific angle to the specific phase of the gait cycle, and you can see the repeated measurements. They do not match, they do not align. This is compared to the slides on the right side, or to the graphs on the right side, this is a fairly close alignment, but it's not exactly repetitions of a gait cycle. So often this mean curve, which you see in red, is used to represent the behavior of the subject in terms of kinematics, like representing the gait cycle of this specific person through a mean value, although each and every stride the person took looks slightly different. So on the right side, this problem unfolds way more visibly into an industrial task. This is lifting, and if you ask a person to repeat a lifting task, and this has been done over 100 times over a 30-minute period, you will see that the kinematic data you capture, and this is true for all technologies we can apply. This is not a technology-based phenomenon. This is a motor control-based phenomenon. It might be related to fatigue, but it might also be related to something totally different. You see that the motion approaches this person takes differs drastically across the 100 trials that you can record. And as you can imagine, if you look at this upper left slide, upper left graph, this is the left ankle tracking of that person. If you represent this through a mean curve, you will have no adequate representation of what happened during this only 30 minutes of recording the motion of the subject. This goes on, not even when you ask one person to repeat the trial, but you ask several people to repeat a similar trial. So this is our own data from a study on exoskeletons. So this is not motion, this is muscular activity data. And I want to direct your attention to the red areas where the red square is. This is the difference between the active exoskeleton being in an off and on state. So on the right, and this data points here, these points are recorded with an active exoskeleton. These ones are recorded with the exoskeleton switched off. So it doesn't provide any assistance in this industrial gripping task. And what we record here is as forearm muscles. So the intended effect should be that with an on state of the exoskeleton, the muscles in the forearm are, so the activity should be reduced. And what you can see is that there's substantial inter-individual variation in motor response. So some people demonstrate the intended effect, others demonstrate no effect at all, and some people even have adverse reactions which were totally unexpected. So they actually increase their motor activity with an active exoskeleton. And this is something that occurs even after people are familiarized with the experimental conditions. So putting this on a larger scale, this is still a fairly small sample, although it's comparatively large to many other studies we see. We cannot predict this pattern of variability ahead of any empirical investigation. So if you look at like the research methodology applied, and this again applies to all the different technologies we can employ using motion capture or motion analysis, you can identify many studies that try to map an effect to an somehow designed intervention in ergonomic studies. Often this is done in a way that you have a sample at a time zero, employ some intervention, maybe apply an exoskeleton, and see how the person changes their movement, their performance, or whatever. And in this way, every person serves as a control for itself. Doing it this way, you cannot be sure that the intervention is actually the cause of that change in motion. So it's would be way more interesting and important to generate evidence through a different study design. And this is called a randomized controlled trial. This is something Francesco has also covered. We need to demonstrate the efficacy and safety of these interventions, possibly long term. So even like employing this over a short period of time is possible, and it's of course possible to extend this over longer periods of time, addressing safety and long-term effects. If you look at the existing literature on any ergonomic setting which employ these kind of study designs, you will hardly find any suitable review within, for instance, the Cochrane database, which is a standard database for, like if you want to check the actual the state of evidence of any medical intervention. And ergonomic interventions translate, at least from their methodological aspects in occupational settings, they can be perfectly transferred to a therapeutic or medical scenario. It's basically the research idea behind this is exactly the same. And what the message is from all these reviews, there are not many, but every single review states that we need further high quality studies to safely address the question whether or not these interventions are first effective and second safe. So summing up, motion capture technology is diverse. We will, as also Pierre-Maria showed, we have a lot of different technologies available, even on mobile devices these days. Their applicability and data quality varies, and they depend on the specific situation to be employed, especially the complexity of the modeling approach. But this is probably just the tip of the iceberg. Might be even more important to consider things like intrasubject variability. So what's up with this variations in repeated, sorry for the typo here, in repeated motor response? This is largely unclear. Many people just regard this as noise, but it's very likely that this is not noise, but actually meaningful, because people who are experts at a certain task demonstrate a different pattern of variability than people who are new at a task. And this is several factors influence this, beginning from expertise, fatigue, and so on. Intersubject movement variability is also a big problem. So group means might be unsuitable for decision making. We need to quantify the adverse, or at least the unexpected effects of the interventions we're looking at. Even using motion capture, we have hypotheses or intended effects we deem, or we seem to address. And if something occurs that is in opposite of what we expect, we cannot average this out and hope for the best, that in all the group effect will be net positive, but we have to move towards a concept that is more oriented towards the medical sciences, where you actually rate and quantify the number of these effects. And finally, the study design, I mentioned that. I think it is often under complex, so we need a more comprehensive study design, probably randomized control trials, especially using motion analysis. This will be more expensive than the approaches taken in the past, but it's, as far as I'm concerned, one of the only ways out of this problem to address the long-term effects of the interventions we apply. And that's the references I've been using. So I'm used to scientific principles, so I'm showing these to you, and thank you for your attention.
Thank you, Christian. Well, I don't know what you think, but I believe that they are killing us. You know, this. We are engineers. We apply. We think that we build effective models, and then we have these guys, you know, killing all our convictions. So we are, when we work in ergonomics, we must be aware that we are walking on the mud, not on cement. So it's still a new field of knowledge. But you know, thank you again. Of course, I'm killing you. Your work is very much appreciated. You know, these guys are in the EAWS scientific committee, so it means that every hypothesis, every model we propose, it's really, you know, toughly controlled and checked, and this is the way it should be. With the technologies we have seen today, and we have also, we had also in the presentation from Maria Pia and from Christian, including the exoskeleton. You know, we collect a lot of data. Now, Christopher Brandl from the Aachen University will talk about data utilization. What do we do with this data, and how we can, you know, exploit and leverage from the availability of this data? Please, up to you. You are on mute, eh? It doesn't happen only to me, you know. Christian? No. Yes, here you are.
Now I'm on mute, right?
No, now we can hear you. It's wonderful. Okay.
Yes, sorry. Wasn't working. So then, hello from me to Hamburg. Also, I will talk about the real-time feedback of motion capture data, and I think I can combine some issues and conclusions Maria Pia and Christian talked about. So I will combine using the biomechanical models with applications. We choose some technology for an application, and so we combine this two stuff within to each other, and we left a little bit the observational methods behind us. I'm also working at a Fraunhofer Institute besides my working on the university in Aachen. So yeah, so now it's working. So I would start with a little experiment on you. So you're on a conference, or the most of you are on the conference, and maybe at lunch you had a high table. And if you think about, you dropped a napkin, and how would you pick up this dropped napkin? If you could think about how would you behave or so. And okay, so usually I'm talking about a lifting technique. If you think about your lifting technique, yeah, there are several techniques which you can apply. Of course, stoop lifting, squat lifting, straddle technique, or something between that. And if you're looking on the compression force on the spine in the area of L5 as 1, then this is one of the main risk factors for musculoskeletal disorders. And as you can see here in the data, usually stoop lifting is more riskful than squat lifting in the point of compression force. And if you're doing a squat lifting, even with 10 loads, with 10 kilogram load, you have a lower compression force than with stoop lifting without a load. So a proper lifting technique can reduce the risk of musculoskeletal disorders significantly. And we all know, and we had talked about before, musculoskeletal disorders are a main issue in our industries in Germany, in US, in the European Union, and we have to work further on that. So what we did as a kind of an application in woodwork. And of course, in woodwork, you have a lot of manual handling of loads, you have forced postures, and so on. And they have defined and implemented a lot of measures to get the work better. And of course, by law, you have to manual load handling training or instructions. But yeah, you can think about if this trainings are effective as a measure. Because we have a phenomenon, and this is called the inert knowledge. And yeah, thinking on the experiment of the first slide, it is, if I ask you which posture or which lifting technique is better or is good, I think you all know which to choose. If I'm asking you like this experiment, and we are all at an ergonomic conference, maybe you will choose also the right one or the good one. But if you are somewhere working and no one is biasing you or nudging you for ergonomics, then usually it is so that your knowledge you have is not applied in practice. And this is the thing why the long-term effectiveness of load handling training is usually not given. So the person will train, and after some weeks, the effect is gone. So what we thought about is to use real-time motion capture feedback for the training. So the feedback is based on scientific findings of Straker, who said that a biomechanical value, it's the peak compression force, is the main risk factor for musculoskeletal disorder. So we used this factor and not an observational methods value for the feedback. And so we have a continuously output. As a technical approach for this area, we have good conditions. I will show you a little live demonstration of this. we have good conditions, we have less occlusions and so on. We took the approach of an optical time of flight sensor with a machine learning algorithm for a markerless calibration-free collection of body posture. Because when we want to apply such things in industry, we have to be with low effort, of course. Afterwards, after this capturing, we use the real-time calculation of the compression force in the area of L5 as one disk, according to a biomechanical model by Jaeger. And then we did a visualization by a force time diagram. So I will show you this now. Here, so as you can see me now, I'm tracked here. You can see that the maximum value of the compression force and the actual or the current value. And now if I'm going like this way and handle this load here, you can see the diagram is going up. So, and if I take another, maybe a better technique, like a straddle technique, yeah, the diagram is, or the value is low. So this kind of feedback gives the persons, the workers, the probability to choose their own lifting technique by training and so on. And we did, of course, a study by that, and we could show that with such systems you can reduce the target value, so the compression force, by approximately 20%. So what we tested a condition without any instruction, so people only lifted a chainsaw. We did an instruction by a standard flyer, which you can see on the right side of the slide. Yeah, I think it's a standard flyer. And then we did a condition with a real-time feedback. And as you can see, the differences in the compression force, in the peak compression forces, ranges from 3.8 to 3.1. Of course, in a group, it's a mean value of a group which we tested, and the flyer condition is somewhere between. So thinking about a clear application in implementing the motion capture plus the model, the assessment model. In this time, we had the biomechanical model of the compression force, could be a good thing to achieve a good application. So thinking a little bit of motion capture in the industry, then of course in the area of occupational safety and health, we have a lot of applications, part applications which are done. Usually, and Maria Pia said it already, we have standards and observational methods which could be supported by motion capture data, but the way should be maybe, or the better way should be from today to go to the digital human model or the biomechanical models, to go with the motion capture data into these models, because then we have a higher accuracy of the assessment, of course. In the part of so-called industrial engineering, of course, human task analysis based on the motion capture data is important. So time characteristics, distributions, so anthropometric parameters, movement and grasping spaces or walk passes, you could analyze with motion capture. Of course, there are a lot of issues, and Maria Pia talked about that, so I will skip the technical issues. Methodically, there are a lot of unknown or unsolved stuff in our ergonomic field. So until now, we don't know how to assess cumulative loading. So amplitude and time together. Is it the force to the power of 2 or to the power of 3, or when you multiply it with the time, or which model to apply for a cumulative load? The interaction between several risk factors are unknown. and also the relative importance of each risk factor, which one is the highest. Of course, these are all stuff which is under investigation. And with more data, more motion capture data, we can come to the answers better. Of course, the accessibility of organizational measures is a methodical issue too. So we can't really assess by value short breaks or stuffs like job rotation. This is really hard to quantify and to assess until now. So these are methodical issues which we maybe can solve about motion capture because we get better data of our working. But in the end, and I was hurrying up a little bit because I think we run a little bit out of time. Analysis and assessment for me is only a means to the end, because what we want to achieve is designing ergonomic work products and processes. So therefore, of course, we need the analysis and the assessment, but the effort should be going into the designing of work situations, of processes, of products. And there are, of course, a lot of other challenges, which I will now read. And I think you in the companies, you have a lot of more challenges than standing here. But I think a really important message for me to tell is that a large number of work design measures are reactive in nature. This is, of course, very important, but the preventive work design, with preventive work design, you achieve more in the long run. However, the preventive approach is subject to the so-called action paradigm, meaning that we have the positive effects that are, the positive effects are mostly not perceived because the negative initial situations are missing. However, preventive work design is really important, and with MTM and our stuff we are doing here, we are trying to get the ergonomics more in the production planning, and I think this is a good way to achieve, and therefore we have to do a lot of work in the scientific and also in the industrial environment. With this, I will thank you for your attention and close my speech.
Thank you, Christopher. We appreciate very much the closing. You know, the planning is important, and the MTM it's for sure an important tool in the planning phase. So thank you. With this last speech, we close, let's say, the scientific part of our event, and now we are going into the companies. And the first. Before opening our final roundtable, I have invited Carlo. Carlo Rubano is a colleague of mine at PwC from Italy, and he's managing an interesting project at Whirlpool, which is a very interesting case because you know, we are touching the planning phase and the execution phase. So it's interesting to see how we did approach the project and the tools we are using. In the final roundtable, we have as a witness, we have invited Manuel Rossi. Manuel Rossi is the industrial director managing some factories from Whirlpool, and in particular the factories where we are running this project. So we can also listen to the voice of the client in this case. So Carlo, we are late. So I give you a very important task to be synthetic. So please pay attention to the stopwatch.
Thank you, Gabriele.
Okay.
Just a second, I will share my presentation. Okay. Can you
Okay.
please just confirm you're seeing the
Yes,
presentation?
yes,
Thank
go
you,
ahead.
Thank you, Gabriel. Thank you for the introduction. And good evening to everybody. I'm Carlo Rubano, and I'm part of PwC operations practice in Italy. So I'll go straight to the subject of this presentation, where today I'd like to introduce an innovative process that we started developing during a project in Whirlpool EMEA, as you said. So we're very grateful for giving us this great opportunity. And the process supports industrial cost controllers and labor productivity continuing improvement pillars. And we call it a productivity management platform. And alongside with this process, we developed an advanced digital solution to support the application. Being involved in many different projects across different industrial sectors, very often we've seen organizations, also the most advanced ones, struggling in linking the results of improvement projects carried out on the shop floor to overall financial indicators. Also, very frequently, especially when the manufacturing processes are geographically distributed with various lines and factories, getting a consistent overall picture of real labor productivity levels turns out to be pretty challenging, and promptly getting the right information out of all sorts of different data sources is complicated and time-consuming. So most times the discrepancies are generated by the underlying labor standards set unevenly across the organization, and it undermines a truly unbiased assessment of productivity measurements. So the productivity management platform aims at guaranteeing consistency between higher level financial indicators and manufacturing level productivity measurements, and to create a digital platform that integrates and qualifies all relevant data sources, and to automate the calculation of KPI at all levels, providing browsable dashboards. In this chart, we outline a typical labor-intensive manufacturing process. Productivity management platform integrates three main data flows. Standard time and line balancing that defines standard work cycles. And this process has to be centralized with a shared data structure. Presence management and production scheduling that defines what should be produced in the shift and the resources that are available. And in this case, in this process, the allocation of workers to workstations is supported by a digital application. And the production and losses collection flow that provides the tally of units produced and production losses. And data are gathered into a cloud-based data lake that feeds cost deployment and continuous improvement pillars. So let's deep dive into the three data flows. The first flow not only defines the standard time for each task, but it also links additional information to the work cycle. So first of all, standard times are set with the MTM UAS or another equivalent MTM system. So we get multi-level data structure and the typical MTM analytic approach. Biomechanical load is evaluated with EAWS, and of course, it is linked to the same structure. The required technical skills are linked to each task. So A standard set of assignable skills is defined and follows the task whenever a rebalancing occurs. And finally, value-adding analysis is performed applying the same application rules across the organization. So all of these steps can be carried out in Tycoon 4, which is the solution of choice for work cycle management in our platform, and allows for a centralized time management governance that ensures the application of consistent standards throughout the organization. This second flow, the presence management flow, provides a detailed mapping of the man hours that are poured into the process. So the actual presence hours are tracked across the plant at line level or at work center level, both for direct and indirect workers. And any deviations from the expected attendance is promptly detected, and the corrections can be made directly by team leaders, who can also manage other daily tasks like absence requests and loan requests from other teams. And the production schedule is retrieved from scheduling systems and linked to standard line balancing. So as we've seen before, information regarding task biomechanical load and the required technical skills are also available for each scheduled batch and workstation. So this means that what is needed to execute the work cycle at each workstation is clearly defined. The allocation process is the step that bridges the gap between production scheduling and execution. So most times the actual allocation of workers to a specific task or a workstation is carried out by the team leaders simply relying on their own practical knowledge of work and people, and in the best case scenario, supported with basic and non-integrated tools. Productivity management platform provides the team leaders with a user-friendly app that suggests optimal work allocation, retrieving all relevant information from the integrated data sources. So during the execution phase, production data are collected directly from MES systems whenever available, or from standardized production reports, and are promptly available for analysis, like cost deployment and improvement project analysis. So productivity management platform and also embeds a comprehensive set of labor productivity KPI based on international standards. Our PwC team has developed a dedicated app to enable productivity management platform process. The application is named Efficiency and Ergonomics Assistant. This application helps the team leaders in carrying out their daily tasks by providing prompt information and full visibility about crew availability, loan requests from other teams, scheduling changes, and etc. Team leaders can also handle workers' present variations directly in-app and manage vacation requests. But let's say that the feature that really makes Efficiency and Ergonomics Assistant stand out is the embedded worker allocation algorithm that proposes the right person to assign to a specific workstation, considering the information linked to a standard cycle and workers' physical characteristics and potential limitations. So let's go through some of the features. I hope you can see. So here we see how this is the scheduled production line, and we can see how to retrieving the information from the standard balancing, the allocation of a worker can be performed directly by the team leader running an algorithm. And it proposes the suitable workers to be allocated to a specific workstation. It is also possible to remove some constraints, or to search into other groups, other teams, and request an operator belonging to another team and handling the processing app. This way, all the modifications are tracked. To make things easier for everyday work, there's also the possibility to recall as default allocation. And we see a couple of other features. This is how we can, how the team leader can manage modifications of the presence, expected presence of the operators. And finally, it is possible to interact with the data and correct any kind of anomaly that is detected by the application to avoid tedious post-execution data cleansing activities. So efficiency and ergonomic assistant, as you have seen, preventively checks the suitability of workers with a certain task, considering all 4 EAWS sections. This means that workers' physical limitations are checked against the 4 EAWS section scores, and that are linked to the specific task. So only the suitable allocation are displayed, and the algorithm is also able to evaluate other constraints that are not directly affecting the biomechanical load, such as the risk for exposure to excessive heat or cold, or working in loud environments. And this kind of risk is also mapped into the system for any workstation. The digital solution embeds a productivity deployment dashboard that is fed with up-to-date shop floor data. They're easily browsable, and they're based on international benchmarks. The dashboard display a set of KPI that recall the world-class productivity deployment models that decompose productivity in the factors, method, performance, and utilization. And the data can be displayed for a single line or at more aggregated levels and into the desired time frame that is dynamic. So productivity management platform brings world-class standards to life by ensuring ergonomic sustainability. It's based on AWS, empowering shop floor managers, enhance the visibility of executive levels because data from the shop floor are available for top levels quickly, and unlock organizations' improvement potentials. All, thank you very much for the attention.